Welcome! In this session, we'll explore an interesting coding problem titled Repeated String Match from LeetCode. This problem challenges us to think critically about string manipulation and repetition. Let's dive in and uncover the most efficient approaches to solve it. The problem we're tackling is called Repeated String Match. In this challenge, we're given two strings, A and B. Our task is to determine the minimum number of times we need to repeat string A so that string B becomes a substring of the repeated version of A. If it's not possible for B to ever be a substring, we return -1. The input consists of the two strings, where A is the string we can repeat, and B is the string we're checking for as a substring. The output is a single integer that represents this minimum number of repetitions, or -1 if it's impossible. Let's look at some examples to clarify how this works. In the first example, we're given A equals ABCD and B equals DAB. The output here is 3. Why? Because if we repeat it 3 times, we get the string ABCD. Within this repeated string, we can clearly see that B equals DAB appears as a substring. Therefore, the minimum number of repetitions required is 3. In the next example, we have a simpler case where A equals A and B equals AA. Repeating A twice gives us AA, which contains B. Hence, the output here is 2. Now let's consider a case where it's impossible for B to be a substring of any repeated version of A. For A equals ABC and B equals WXYZ, no matter how many times we repeat A, we can't create a string that contains B equals WXYZ. This is because the characters in B don't overlap with any part of A. As a result, the output is -1, indicating that forming B as a substring is impossible. These examples help demonstrate both possible outcomes, when we can find the minimum repetitions and when it's not feasible at all. Let's wrap up by looking at the constraints and some additional edge cases. The lengths of both A and B can be up to 10,000, so we need an efficient solution. Both strings consist of lowercase English letters. Now, for edge cases, if A and B are identical, the result is 1 because no repetition is needed beyond the original A. If B is much longer than A, we might need to repeat A several times to check for a match. For instance, if A equals ABC and B equals ABCAP, we would need to repeat A 4 times. On the other hand, if none of the characters in B are in A, it's immediately impossible to form B, and the result is -1. Keeping these constraints and cases in mind will help us design an efficient solution for the problem. To solve the problem of determining how many times string A must be repeated such that string B becomes a substring, we consider a brute force approach as an intuitive starting point. The idea here is simple. We repeatedly concatenate string A to itself until the resulting string is long enough to potentially contain B. After each concatenation, we check if B appears as a substring within the concatenated result. If it does, we return the number of repetitions of A. If the concatenated string becomes excessively long, specifically, more than twice the length of B plus the length of A, we can safely conclude that B cannot be a substring, and we return -1. This approach is straightforward but computationally expensive, with a worst-case time complexity of O, n*m, where n is the length of A and m is the length of B. While simple, it lays the foundation for understanding the problem constraints and limits. A more efficient approach eliminates the repeated concatenation process by directly constructing the minimum required repetitions of A. If B can appear as a substring, it must be fully contained within a repeated version of A that is at least as long as B, or it may span across the boundary of the repetitions. To handle this, we first calculate the minimum repetitions of A needed to cover B using the ceiling of len B/len A. We then construct this repeated string, call it repeated_A, and extend it by one more repetition to create repeated_A_extended. This extra repetition accounts for cases where B overlaps across the start and end of A. Next, we simply check if B is a substring in either repeated_A or repeated_A_extended. This method is computationally more efficient as it avoids unnecessary concatenations, with the time complexity primarily determined by the substring checks and the construction of the repeated strings, yielding a complexity of O, k*n, where k is the number of repetitions. For further optimization, we could use advanced algorithms like KMP for substring search, which reduces the substring matching to O, n plus m. However, given Python's efficient substring operations, the KMP approach may add unnecessary complexity without significant practical benefits. The chosen strategy for this problem is the optimized approach using string repetition and substring checks. This method strikes an excellent balance between efficiency and simplicity. By recognizing that the maximum repetitions required are limited to ceil, len, b/len, a, plus 1, we avoid the inefficiencies of the brute force method, which requires repeated concatenations. At the same time, this approach avoids the complexity of implementing the KMP algorithm, relying instead on Python's built-in substring operations, which are highly efficient in practice. The trade-offs are clear. While the brute force approach is easy to understand, it is computationally expensive, and while the KMP algorithm is theoretically optimal for substring search, it introduces unnecessary overhead for this specific problem. The chosen approach delivers an optimal solution with minimal code complexity, making it particularly suitable for competitive programming scenarios where simplicity and efficiency are key considerations. To tackle the problem of determining the minimum number of times we need to repeat string as such that b becomes a substring of the resulting concatenated string, we start with a clear step-by-step approach. First, we initialize two variables, a string variable called repeated, which starts as an empty string, and a counter called count, which keeps track of the number of times a has been appended. These will help us build the concatenated string incrementally while tracking the number of repetitions. Next, the iterative process begins. We append to the repeated string and increment the count variable by 1. After each iteration, we perform a substring check to see if b is now contained within repeated. If it is, we can return the current value of count as the result, since it represents the minimum repetitions needed. This simple framework allows us to systematically build the solution while checking for the presence of b at each step. Next, we consider edge cases and ways to optimize our algorithm. If the length of b is significantly larger than a, we know that a must be repeated a minimum number of times to even have a chance of containing b. Specifically, this minimum can be calculated as the ceiling of the division between the lengths of b and a. For efficiency, we can perform an initial check to repeat it enough times to meet this threshold. However, even after this, if b is not found as a substring in the concatenated result, we add one more repetition of it to account for possible partial overlaps. If b is still not a substring at this point, we can safely return -1, as it indicates that b cannot be formed using repeated a. Additionally, if the characters in b include any that are not found in a, it's immediately impossible for b to ever be a substring of a, and we can return -1 without further computation. These optimizations ensure that we handle edge cases efficiently and avoid unnecessary iterations. To better understand the algorithm, it is useful to highlight some key insights. First, the substring check using Python's an operator is highly efficient, operating in O, n plus m, where n is the length of the concatenated string and m is the length of b. This eliminates the need for manually iterating through potential matches, saving both time and effort. Another important insight is the calculation of minimum repetitions. To guarantee that b can potentially fit within repeated a, we must repeat at least the ceiling of the division between the lengths of b and a. We also add one extra repetition to handle cases where b overlaps across the boundary of repeated a. Finally, checking for edge cases up front, such as whether b contains characters that are absent in a, allows us to terminate early in scenarios where forming b is logically impossible. These insights collectively make the algorithm both efficient and robust. The algorithm relies on simple yet effective data structures and operations. The primary data structure is a string variable called repeated, which stores the concatenated result of repeating a. Strings are particularly well suited for this problem because they directly support substring operations, which are central to our solution. We also use a counter variable, count, to track the number of repetitions, enabling quick access to the result when the substring condition is met. Key operations in the algorithm include string concatenation, where each iteration appends it to repeated. While string concatenation in Python is efficient, in lower-level languages, this step can be further optimized using string builders or similar tools. Another critical operation is the substring search, performed using Python's an operator. This operator provides an optimized way to check if b is a substring of repeated, eliminating the need for manual iteration and improving runtime efficiency. Together, these data structures and operations ensure the algorithm remains both simple and effective. Analyzing the algorithm's complexity provides a clearer picture of its performance. The time complexity in the worst case is O and *m, where n is the length of string A and m is the length of string B. This accounts for both the repeated concatenation of A and the substring search operation. While this might seem costly, the use of optimized substring search ensures that the algorithm performs well in practice. The space complexity is O, k*n, where k represents the number of repetitions required to make repeated long enough to potentially contain B. This space is needed to store the concatenated version of A. By balancing efficient operations with proactive edge case handling, the algorithm achieves a good trade-off between time and space complexity, ensuring it is practical for a wide range of input sizes. The solution to LeetCode problem number 686, repeated string match, determines the minimum number of times string A must be repeated such that B becomes a substring of the resulting string. First, we calculate the minimum number of repetitions, min_repeats, required to ensure the length of the repeated string is at least the length of B. This is done using the formula len b // a, which is an optimized way of computing the ceiling of the division. Next, we check if B is a substring of the string formed by repeating A the calculated minimum number of times. If true, we return min_repeats. If B is not found, we check again by repeating A one more time, min_repeats plus 1. This accounts for cases where B might overlap the boundary between repetitions of A. If B is still not found, we return -1, as it means B cannot be a substring of any number of repetitions of A. This solution is efficient, as it ensures the string repetition and substring checks are minimized. The algorithm handles edge cases, including when B is longer than A or when B cannot be formed by any combination of A repetitions. Here, we are implementing the solution to the problem in Java. First, we calculate the minimum number of repetitions of string A required for string B to potentially be a substring. This is done by dividing the length of B by the length of A and rounding up, which ensures that we have enough characters to check for a match. Next, we repeat string A this minimum number of times using the repeat method and store the result in a string builder. If the resulting string contains B, we return the minimum number of repeats since it confirms B can be formed with these repetitions. If not, we append one more repetition of A to the string builder and check again. If B is found this time, we return min_repeats plus 1, indicating that one extra repetition was necessary. Finally, if string B is still not found, we return -1 to indicate that it is not possible to form B by repeating A. The main method includes some test cases to demonstrate the implementation. For example, when A is ABCD and B is dab, the output is 3 because repeating ABCD 3 times forms a string that contains B. When A is at and B is AA, the output is 2 since A needs to be repeated twice. If B cannot be formed at all, like in the case where A is ABC and B is WXYZ, the output is -1. This completes the implementation and testing of the solution. In this example, we are given A as ABCD and B as dab. The first step is to calculate the minimum number of times we need to repeat A so that it could potentially contain B. Using the formula min_repeats equals len b / len A, we find that the length of B is 8 and the length of A is 4. This gives us min_repeats equals 2. Next, we construct a string by repeating A twice, which results in repeated equals ABCD. At this point, we check if B is a substring of repeated. Since dab is not found within ABCD, we need to add one more repetition of A. This updates repeated to ABCD by appending another ABCD to it. Now that we have updated repeated to ABCD, we check again if B is a substring of this new string. This time, dab is found within ABCD, so we can conclude that we need min_repeats plus 1 repetitions of A to contain B. Therefore, the result is 3. In the next example, we look at a case where it is not possible for any number of repetitions of A to contain B. Here, A is ABC and B is D. First, we calculate the minimum number of repetitions. Since the length of B is 1 and the length of A is 3, we find min_repeats equals 1. Repeating A once gives us repeated equals ABC. Checking if B is a substring of repeated, we see that D is not found in ABC, so we proceed to the next step. To continue, we add another repetition of A to repeated, resulting in repeated equals appcap. We then check again if B is a substring of this updated string. Since D is still not found within appcap, it becomes clear that no number of repetitions of A can ever contain B. In this case, we return -1 to indicate that it is not possible for B to be a substring of any repeated version of A. Finally, we have an example where the input A is A and B is A. Using the formula, we calculate min_repeats as 5 because the length of B is 5 and the length of A is 1. Repeating A 5 times gives us repeated equals A. Once we construct repeated as A by repeating A 5 times, we check if B is a substring of repeated. In this case, A is exactly equal to A, so we can directly conclude that the minimum number of repetitions required is 5. Therefore, the final result for this example is 5, as no additional repetitions are necessary. This demonstrates how the solution handles cases where B is an exact match within the minimum required repetitions of A. Here, we analyze the time complexity of the solution step by step. First, calculating min_repeats involves a simple arithmetic operation, specifically the ceiling of len b/len a, which is done in constant time, 1. This step doesn't significantly contribute to the overall complexity. Next, we create the repeated string A** min_repeats, which requires duplicating the characters of A multiple times. Since min_repeats is roughly proportional to len b/len a, this step takes len b time in total because the length of the resulting string is approximately equal to len b. Finally, we check if B is a substring of the repeated string. This substring check is the most computationally expensive step, as it involves comparing up to len b characters of B against len repeated characters of the repeated string. In the worst case, this operation has a complexity of len repeated *len b. Since len repeated can grow to len b plus len a, the complexity simplifies to len b plus len a *len b, which is dominated by len b caret 2. If B is not found in the initial min_repeats repetitions of A, we add one more repetition of A to the string. This increases the length of repeated by len a and requires another substring check. However, the asymptotic complexity remains unchanged at len b caret 2, as the additional repetition doesn't significantly affect the order of growth. Therefore, the dominant factor in the time complexity remains the substring search, which makes the overall worst-case time complexity of the solution len b caret 2. Shifting to the space complexity, the main contributor is the memory used to store the repeated string, which grows to a maximum length of len b plus len a. This means the space complexity is proportional to len b, given that the size of repeated is primarily determined by the length of B. The substring search itself does not require additional memory beyond the space already allocated for repeated in B, so it does not impact the space complexity beyond this. In addition to the repeated string and the substring search, we use a few auxiliary variables such as min_repeats and repeated. These variables occupy constant space, 1, and do not depend on the size of the input. Combining all these factors, the final space complexity is determined by the memory required for the repeated string, which results in len b. Next, let's consider the best, average, and worst-case scenarios for this problem. In the best case, B is found within the initial min_repeats repetitions of A. Here, the substring check completes early, and the time complexity is dominated by the string repetition, resulting in len b. In the average case, the position of B within repeated determines the complexity, but it often approaches the worst-case scenario. Finally, in the worst case, where B is not found until one additional repetition of A is added, the time complexity reaches len b caret 2, as the substring search is repeatedly performed over a growing string. To understand the advantage of the optimized solution, let's compare it with a naive approach. The naive method involves repeatedly appending A to a new string until its length exceeds len b, and checking for the presence of B after each addition. This results in a much higher time complexity of len a *len b caret 2 due to the repeated concatenations and substring checks. In contrast, the optimized solution calculates the required repetitions upfront, significantly reducing the number of substring checks. This leads to an improved time complexity of O, len, b, caret 2. Finally, let's confirm the big O complexity mathematically. The substring check is the dominant operation, as it involves a sliding window comparison over the repeated string. In the worst case, this means comparing all characters of B against potential substrings of repeated. This results in a quadratic time complexity of O, len, b, caret 2, which aligns with our earlier analysis and confirms the efficiency of the optimized approach. When working on this problem, there are a few common mistakes to watch out for. First, not handling edge cases for string B can lead to incorrect solutions. For example, if B contains characters that are not even present in A, or if B is so long that it cannot fit within any reasonable number of repetitions of A, then B can never be a substring of the repeated A. To avoid wasting time, you should check for these cases up front before attempting concatenation. Another mistake is creating an infinite loop with a brute force approach. Without a clear termination condition, repeatedly concatenating A can lead to inefficient or endless processing. To prevent this, you can use the length of B to calculate an upper bound for how many times A needs to be repeated. Lastly, there's the off-by-one error in calculating repetitions. If you only repeat a CL, len, B, /len, A times, you might miss cases where B straddles 2 repetitions. Always add 1 extra repetition to ensure you've covered this scenario. Another common pitfall is incorrectly checking for substrings. Some solutions mistakenly use equality comparison instead of substring search. Remember, B does not need to equal the repeated A, it only needs to exist within it as a substring. To fix this, use proper substring search methods like Python's an operator or Java's .contains. Additionally, inefficient string concatenation can also slow down your solution. Using plus equals or similar operations in a loop is problematic because strings are immutable in most programming languages. This means every concatenation creates a new string in memory, leading to poor performance. Instead, use more efficient methods like joining lists in Python or using String Builder in Java to handle concatenations. When preparing for interviews, it's helpful to recognize key patterns and problems involving string repetition. For this problem, the critical insight is that B must align within at most 2 repetitions of A. This understanding can simplify your approach. In terms of complexity, the brute force method has a time complexity of O and *m, where n and m are the lengths of A and B. However, optimized approaches can reduce the number of concatenations or leverage string matching algorithms for better performance. Additionally, it's important to clearly communicate your assumptions during an interview. For example, you should explicitly state how you're addressing edge cases, such as when B contains characters not in A or when B is excessively large. Finally, while debugging, start with small test cases to verify correctness before scaling up to larger inputs to evaluate efficiency. This problem is closely related to several others in string manipulation. For example, LeetCode 28, which involves finding the first occurrence of a substring in a string, provides foundational knowledge that can be applied here. Of course, LeetCode 686 is the problem we're solving, but LeetCode 214, which involves finding the shortest palindrome by string concatenation, and LeetCode 459, which checks if a string can be formed by repeating a substring, are also relevant. Exploring these problems can deepen your understanding of string manipulation patterns. One alternative approach to solving this problem is the sliding window technique. Instead of fully concatenating the string, this method simulates the repeated string while sliding through B. This saves memory and can be implemented with a time complexity of O and plus m, where n and m are the lengths of A and B. To further optimize substring search, you could use the Knuth-Morris-Pratt, or KMP, algorithm. This method pre-processes the pattern to create a partial match table, reducing redundant comparisons and improving efficiency. While KMP achieves a time complexity of O and plus m, it does require additional space for the pre-processing step. Another advanced approach is to use hashing, such as the Rabin-Karp algorithm. This technique is useful for efficient substring search by comparing hash values rather than the actual strings. However, it comes with trade-offs, such as potential hash collisions or additional complexity in computing hashes. Both of these methods, KMP and hashing, offer O and plus m performance in most cases and are worth mastering for problems like this one. Great job following along. To wrap up, we covered the key aspects of solving the repeated string match problem, including the brute force approach and its complexity. Remember, mastering string manipulation is essential for coding interviews. Don't forget to like and subscribe for more tips and solutions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!